So I'm recording this, and hopefully the rest of you guys will be joining us soon. Before we begin this lecture, how many of you use a GPU before? That also include playing games. Well, that's only a few of you. Yep. So we all use a GPU before. That includes myself as well. I play a lot of games. Back in the days, I still play quite a few games today, these days. So I've been using GPUs a lot. It's actually one of the primary reason why I went into computer engineering. Actually, I was playing games when I was in high school, middle school, and at some point I'm like, okay, I'm curious how to create like a game, and I don't know what happened. It just suddenly to be honest, I don't really have a lot of artistic skills or creativity, so I dig deeper into like the hardware side of things, and I'm curious like how the GPU works. Uh, so today we will learn how the GPU works based on the knowledge of what we learned so far. While I'm going to say that this is a little bit of a unique topic in the sense that you're in most of the computer architecture class for undergrad, unless you're in the United States, right? They're not gonna cover this topic, but this is one of the topics I feel like is more important as time goes on. The reason behind it is not just because we still play games, like obviously. And what are the other really, really popular things that people use GPU nowadays? Can someone give me some examples? Actually, there are multiple. What are the applications that people use the GPU for? Crypto mining, yes, that's one of them. Actually, these days, if you use GPU for mining, you actually will lose profit. Anyone want to guess why? There's specialized hardware for it. Actually, that's even more performance in some sense, right? They will shine, yes. And also because you just can't come up with a power plant that's free. It's actually consumed too much power that you pay too much of the electric bill than what you gain from mining. So in the end, it's like, okay, I think if you recall in 2018 or 19, there'll be a lot of like secondhand 1080 Ti on eBay. A part of it because people use it for mining. I do not recommend you to buy those things because those secondhand GPUs have been overclocked and used and abused, and yeah, it already have a lot of wear and tear, so don't buy them. But yeah, that mining is one of the used to be a popular application that people use the GPU for. What else? I think a lot of you are taking that class actually right now in ML. Yes. So deep learning has been popularized GPU for what we call general purpose computing, right? So these are the applications that drive the demand of new types of hardware. Google, for example, came up with their own like Tensor Core, where they came basically they say, okay, I want to build the hardware to do deep learning. I don't want to rely on NVIDIA's GPU anymore. A lot of other companies are also doing that. How many of you watched well, I think I might have asked this question last week, but if you watch the iPhone 12 launch video, you see that there's a diagram of the chip, right? And there's a brief period of time they're trying to put in like, okay, these are different things we put in on top of just the CPU. Obviously, there's a GPU in there, and there's also a bunch of like neural accelerators, which basically do matrix multiply and linear algebra operations. So I hope you are at least now a little bit more motivated. I'm not gonna say you will be excited about hardware. That I know where it is, right? So it's is a pretty unique topic for a really small group of people. But hopefully now you would be more willing to learn what's actually inside the GPU. So in a modern system, right, these are, well, here's a picture of RTX 1080 Ti, which you can buy. And I wish I have the money to buy them. I do not, right? But if I have these cards, what I can do is I can play a bunch of games, right? These are some, well, actually now I play all of them. So these are games that you can play using the GPU, right? And if you have a card as powerful as this, you can basically adjust the graphic quality to the maximum, and you enjoy, right? Pretty surreal experience. And one thing that I have not realized until I actually played a game for 5 years, like from 5 to 10 years ago, and then basically I switched to the game that's out right now. One thing that you will realize is how much graphic improved, right? And how much they assume that the hardware will be capable of drawing those things. A lot of them comes from the fact that the modern GPU can do a lot more compute per cycle. You can do a lot more add, a lot more multiply. But that's not only the only thing GPU can do. Over here, there's a lot of other things that GPU is able to provide, right? Uh, Linear algebra application obviously is being used in a bunch of different, I guess, types of bigger applications like ML, for example, ML, machine learning application, FFT. So if you look at fast Fourier transform, anyone want to take a guess what FFT is used for? Oh, sorry, this thing, fast Fourier transform. So anyone heard about image processing application? Like image, actually anyone used Photoshop before? Yeah, so a lot of the Blender, I think, also use a lot of these libraries. So one of the key techniques that if you're in a more like a computer engineering program, one of the big area in there is what we call signal and system. What's actually inside is we study maths, right? And what happened is a lot of operations that you have to do in the 2D space or even 1D space in acoustic, right? When you need to process music, what happened is everything is actually frequency based, right? So a lot of the integral and the maths differentiate turns into multiply and add and subtract in the frequency domain. But the way to convert the data from a time domain into a frequency domain is through this thing called fast Fourier transform. So if you study math like last year of high school, I think uh, some program will cover this thing called Fourier transform, and you'll be like, why the heck do I need to study these bunch of integral, right? This is the reason. It's actually once you convert to frequency domain, a lot of things will be really fast. You can do a lot of image processing application, acoustic-based application that has to do with a lot of music uh, conversion, the way you want to amplify certain signals. You want to actually come up with your own noise canceling headphone, right? You can do that in the frequency domain. The theory behind it is actually not that complex. You want to cancel the signal. So you have a microphone that listens to the signal and you generate the negative version of that to have a flat signal at the end. Right. So obviously cuDNN for deep learning. CUDA Blast also is used for a bunch of machine learning application. TensorRT obviously is now Tensor dealing with TensorFlow, right? So these are different libraries that you can use, apply, and accelerate your application, make it faster. Outside of machine learning, a lot of other things that people have been doing are, for example, self-driving car, right? How many of you heard about the application called SLAM, SLAM? Yes, no? It's okay to say no. I mean, these are what a lot of developers are dealing with right now. SLAM is what is an it's one of the application that take in your surrounding data. So if you have a self-driving car or a drone, right? What happen is they'll have a bunch of camera around them, and SLAM basically would take a look at all the camera, including the image sensor and the lidar. Uh, lidar sensor basically you can detect how far from between you yourself where the sensor is and the object. And based on that, they built the 3D environment around you so that you know where to go. Basically, it allows you to navigate your surroundings. There's also another different application called 3D point cloud, where it's also used to detect your surrounding, right? These things will be more complex than your like home what's it called, the vacuum robot, right? That just go around, and when it hits something, it builds the map based on that. It hit the wall, you draw the wall. These things actually have a sensor to actually build all the surroundings. And SLAM is like a part of the bigger application that's being used in a lot of like things like self-driving car. Image processing, Photoshop, as I mentioned earlier, there is a certain part of Photoshop that requires a lot of high throughput uh, image processing libraries that requires, not requires, but can benefit from things like a GPU as well. Rendering an animation also requires a lot of GPU power. So these days, if you look at, okay, if you buy a fancy GPU, this is actually now an old GPU, right? The Titan X is older. Right now, you would notice that the new generation is called A100. Uh, with these, it allows you to have a GPU in the cloud and share them amongst multiple users. My thesis actually addressed some of the things that NVIDIA claims they can do, but actually are not efficient yet. Uh, I will, toward the end of this semester, I'm going to talk briefly now that I introduced both virtual memory and the memory system and the GPU. I'll talk a little bit, maybe even an hour, about some of my work on how to make your NVIDIA GPU better. But these days, one thing you notice is GPU gains a lot of popularity through whatever we call massive parallelism. So we will learn today what does it mean, right? So there are three fundamental concepts behind the GPU. The first concept, you might have heard about this from news or hacker, some like the like Reddit or like uh, web board that have a bunch of like hackers and developers lingering and talk about the GPU. The concept is called SIMD, single instruction multiple data. It's actually a pretty simple concept. We will talk about this before we dive into the GPU. The second topic that they do is called fine-grained multithreading. Anyone remember this thing? We talk about this right before we talk about branch prediction. So if you do not, you have a recap of what is fine-grained multithreading. Also, predicated execution. We also said this and talk about this right before branch prediction or right after. But basically, I'm going to cover this topic again. So now, since these two are already brought up, so I'm going to talk about these two in detail as a review. So we go a little bit quick on these topics. But before we begin, let's discuss something about parallelism. So these days, obviously, everyone's computer, including your phone, has multiprocessor. It has multiple cores. The reason behind that is there's a benefit on running multiple things in parallel, right? So now let's go back to our lecture on how to measure your performance. Like one of the key performance that we want to measure is called instruction throughput. What is that? It's basically the measurement of how many instructions you can retire. Retires mean you finish the write back. How many instructions you can retire within a unit of time, right? So if you want to know the upper limit, and assuming load store is free, you can check the clock speed. And then you can check the issue width. Issue width is basically if you can fetch more than one instruction per cycle. For example, these days CPU, it fetch 2 or 3 or 4 instructions in a cycle. It's capable of doing that. And then the problem here is there are multiple things that we need to discuss. Obviously, memory is not free. We will talk about this after the GPU lecture on how much is the overhead of going to the main memory. But right now, I'll just say it's a lot. And another topic is when you have parallelism. So if you took the OPL class, or if you are taking the OPL class right now, you will realize that there's a benefit to having or being able to run things in parallel. If you took the OS class, obviously you also cover multi-threading, right? But parallelism means that you do multiple things at once. This is basically simultaneous execution of computation, right? And they don't have to be related, but they can be related instruction. In the GPU, we will be focusing on the second bullet point because it's not just have to be related. It not just have to be from the same application. It has to be the exact same instruction. That's how much of the constraint that the GPU manufacturer like NVIDIA doesn't really tell you when they want you to buy their GPU. When you buy the GPU and expect that somehow things would run really quickly, you implement it the way you implement the CPU program, voila. It's slow. It actually can be really slow. So we talk about data flow diagrams, so we're not going to cover it in this class, but just be aware that that's related to parallelism. In terms of concurrency, concurrency is a little bit different from parallelism. If you took OPL, you know about this. If you are taking functional and parallel programming, this is actually one of the topics I'm going to talk about this Friday. So be aware of that. If you haven't taken any of the two classes, concurrency is basically the fact that you can handle multiple things at once. The things that computer do should be independent of each other. Why is that? You don't really want to synchronize between a bunch of concurrently running threads, right? It's like when you have two humans performing certain tasks. You don't really want them to have a lot of synchronization point because the two have to talk to each other all the time and try to figure out, okay, what's your progress? Can I do this? Can I do that? And that can be slow. Think about it this way, because concurrency is a process of truly running things independently on the hardware level. And if you're curious, this is a link that you can go and check out. It's a talk that in the Go language, the language that Google introduced and is actually support a lot of paradigms that allow you to do run parallel program. It's a blog that talks about, it's a video actually, it's a video of a talk that talk about what is the difference between concurrency and parallelism. And these are some examples. You see, you can use Silk for parallel for loop. You can use OpenMP for to annotate saying, hey, this for loop can be done in parallel, right? And notice that there's no dependency. My B of I doesn't depend on A of I minus 1. It doesn't depend on the previous iteration of my loop, right? So these things determine how much you can run things in parallel. And that's Amdahl's laws. I'm not going to repeat Amdahl's laws so many times, but basically, the performance speed up depends on serial and parallel parts. So you want to have your algorithm, right, design it such that it can be parallelized, it can be run in parallel. And the zero portion would be what becomes the critical bottleneck to your performance. Here's the paper, and the critical section, if you look at works that are being introduced these days in year 2020, we talk about critical section not just because of the single thread part, the zero portion, but also there are other parts that can become critical section, right? Things that have synchronization like this, or when you have shared data, right? Let's say you have a shared linked list, someone wants to modify the list. No one else should be able to access that list because they are still being modified. It's like you have a highway in a real life scenario, right? You have a highway. You need to fix the highway because there's some potholes. What you want to do is you want to close out the highway so you can fix everything before you open the highway for someone else. The exact same thing. You have parallel thread running. You want to make sure no one else can access that shared data if someone is modifying it. So now that we talk about parallelism, let's review two of the concepts real quick that we covered already and introduce a new concept called single instruction multiple data. So the first thing we are going to review is fine-grained multithreading. Right, so in the traditional multithreading, each thread is assigned to run on one of the CPU. These days, if there are 4-core CPU, then you can run 4 threads on the 4 CPU. If number of threads is greater than the number of CPU, you basically allow the thread to take turns to run on the CPU. You context switch between one thread to another by either using the OS or use the hardware. Hardware can support multi-threading as well. The way they support it is to have a different copy of all the architectural states, a different copy of the program counter, a different copy of the register files, a different copy of the pipeline register, depending on each thread, right? These, the way you switch between threads can impact performance. So what about hardware multithreading? Right? Let's say you have a CPU, just one CPU. You can still run multiple hardware threads on the CPU, and here's why. Right? Why are we only executing? So actually, the question I want to ask you is this: why are we only allowing us to have one thread of execution? The reason is we don't have unlimited die area. Right? You can't just say I'm gonna add 1 trillion more transistor on your die without making your CPU look this big, right? It's going to make your CPU looks too big. When the CPU becomes too big, you need to then manage the heat dissipation. You need to manage how you're going to drive all the electrons inside the CPU. Everything becomes too complex and too much overhead to actually implement the CPU. So our idea is, well, if having multiple threads are complex, why don't we just have a few of those? 2 threads that can run in parallel, not exactly parallel, but they context switch really fast. You have a different copy of the program counter and the pipeline register. And each threads basically run different processes, right? So that they can run a totally different program, which means there's no dependency between the 2 programs. The benefit here is you can have one CPU that runs many things in parallel, right? Everything becomes context switch. You switch multiple threads, they all share this one CPU. The concept called simultaneous multithreading basically say, okay, if I have a processor that is waiting for a cache miss, if I'm waiting for a cache miss, what can I do? Okay, what happened? What happened? Let me ask you this question. So please answer. If you facing out because I've been monologuing for a while, please answer. What happened if I have a cache miss? So there are 2 questions, right? the first question is what need to be done? You want to go access your data. My second question, which please answer, is do I have to start the pipeline? Do I have to start the pipeline? If I have a cache miss, I'm waiting for my data. Yes, no. Yes, no. Come back, guys. Don't leave me alone here. Yeah, okay. Thank you so much for answering. Yes, you actually do have to start the pipeline unless so both answers are correct depending on your processor. If you have single thread, single CPU, yes, you have to start the pipeline. But if you have another hardware thread, what you can do is when you have a cache miss, you are waiting for the data, the CPU switch to another thread so that you can run something else and so that you don't have to store the pipeline. This is actually available in a lot of your CPU these days. I guess depending on whether you do the top, like buy the top end CPU versus the middle end, like a lower end CPU. For example, if Intel hyperthreading allows you to have one more thread, whenever you miss in the cache, you can switch to that thread and the pipeline becomes full. What are the trade-offs? The trade-offs basically now you have to support them, right? So you need to have a different copy of PC program counter and a different copy of the pipeline register, the register files, just to make sure that when you switch back, you can resume your program without the user noticing, right? Now let's talk about fine-grained multithreading. So fine-grained multithreading that's being used in the GPU is this. The idea is this. When you have any pipeline stall period, switch to a new thread, right? So if you have, say, a 5-stage pipeline, you need at least 5 ongoing hardware threads if you want to cover things like a cache miss, which has to go to the memory. It means that you now have to have hundreds of available hardware threads to switch, right? So with limited DRAM bandwidth, this is not really exactly 100 number of cycles. You can actually, this number can go up even more, right? But basically, fine-grained multithreading, if you have a 5-stage pipeline, fetch, decode, execute, memory, and write back. Let's say this is thread 1. This will be having thread 2, thread 3, thread 4, and thread 5 running. When thread 1 is done, thread 2 move here, thread 3 move here, thread 4 move here, thread 5 move here, and now you fetch thread 1 inside, right? So this allows you to always having something active in the pipeline at the same time. The downside is if you look at, say, thread 1's own performance, this is going to be really bad. Thread 1 will finish in every 5 cycles instead of every cycles. So on top of this, you need extra logic to keep all the threads context, right? So this is actually incur high overhead and you get low single thread performance. The second concept we talk about is called predicated execution that I mentioned. This is available in ARM processor, for example. Let's say you have a sample code like this. When you handle branches, right, you can do branch prediction, obviously. Another way you can do this is called predicated execution, where you convert your control dependence, the fact that you cannot predict where you're branching to, that becomes data dependence. Data dependence because if the outcome of your compare operation becomes true, you do this. Otherwise, you put in bubbles. You don't execute that code and execute whatever is in the else statement, right? So conditional execution in ARM ISA would have a way to check whether it's true or false. If it's true, you do a certain block of code. If it's false, you do another different block of code. And the benefit is now you can get rid of branch prediction. It allows code optimization, but then this can cause useless work, and this requires additional hardware support. right? Any questions so far about fine-grained multithreading and predicated execution before I go into SIMD? Because once we know these three, we know how the GPU works. It's actually as simple as that. All right, assume there might be questions later, but if there's no questions right now, let's dive into SIMD. Basically, SIMD is coming. Basically, the reason why you might want to use SIMD is one of the observations that we have math operations. They are done on a lot of data. And sorry about the lack of animation. Basically, I want to animate one bullet point at a time, and then I forgot to add any animation in. Basically, you have vector add or vector multiply, right? What happened? There's just a bunch of adds and a bunch of multiply. They are the exact same opcode, right? It's just that the data are different. The data are different. You want to add A0 and A0 and B0. You want to add A1 and B1. You want to add A2 and B2. The operations are the same. It's just a bunch of adds. The idea behind the GPU is this. Well, if you know that it's the same instruction, why don't you get rid of the decoder, get rid of the fetch, and just add tons of execution units? So when you have one fetch, one decode, 32 adders, 32 multipliers, what will you get? Basically, when you fetch one instruction, you can do 32 add at the same time. Right? You can do 32 add at the same time. This concept is called SIMD, or single instruction, multiple data. These days, you might also heard about SIMT, single instruction, multiple threads, where all the threads execute the same instruction. They operate on different pieces of data. Notice that your program counter has to point to the same instruction. Anyone want to guess the downside of this way to execute your program? Obviously, yes, your ISA has to be a little bit more complex because you have to support the fact that you need to kind of group things together. Another fact is you need to basically come up with the parallel program. So you need to be well versed in parallel algorithm, right? You need to find an algorithm that do things in parallel. It's not even that. You need to find an algorithm that ended up using the same instruction, right? Using the same instruction. So what type of, so let's say I have something, let's say I look at two algorithms. The first one do a lot of matrix multiply. The other one are doing breadth first search. Which one is likely to be more friendly for SIMD between the two algorithms? Matrix multiply or breadth first search? Matrix multiply. The reason behind is obviously you know that when you do matrix multiply, you take an array, you multiply that number with another array, right? And that's it. Once you're done, you do a bunch of add. So the algorithm by itself is obviously really, really friendly towards SIMD. So the GPU is essentially SIMD plus fine-grained multithreading. It's actually as simple as this. If you understand how fine-grained multithreading works, if you understand how SIMD works, you fuse the two together and you got your GPU. The way you design the actual GPU will be a little bit different. There are variations, but conceptually, this is how the GPU works. So let's look at the GPU core starting from the software point of view, right? How many of you take the deep learning class right now? Okay, So are you dealing with a CUDA program or OpenCL program, or are you just calling libraries from Python? Oh, okay, you use Colab. All right. So Colab is a little bit it prevents you from having okay. Keras is also another good tool that you can try out deep learning without having to know CUDA. Keras or like a Colab GPU, at the end of the day, the last layer is written in CUDA. CUDA is a program, it's a language that allows you to program things in using a GPU. The way it looks close to the C++ language. One of you actually submit the matrix multiply code in CUDA for me in open, I'm not open, in OPR, right? So you know how to write things in CUDA. To some extent, you've seen it before. Basically, it looks kind of like C, but with a bunch of different API calls that you have to use, or you might have to add hints toward the compiler, which allow the compiler to tell how to configure the GPU. So let's say you have a CUDA program. If you go further to the left, you start with Colab GPU or Keras. That get converted to CUDA or OpenCL program. Are you all with me? Basically, everything at some point will be converted to this. So that's the software. The program that you get, it consists of multiple threads that we call a thread block. Multiple threads that we call a thread block. These threads consist of the almost exact same assembly code, but they operate on different pieces of data. So these are the big assumptions. Similar assembly code in GPU assembly. And then they are operating on different pieces of data. In this row, we call a warp, and the warp will play some roles in a bit. Just sorry. Just know that when you have a program, they'll be broken down into a lots of threads. When I said a lot, this can be thousands of threads, hundred and thousand of threads. Then each thread will be grouped into what we call a grid. A grid in software or a thread block in hardware, they are the same thing. Then inside the thread block, there's a unit called a warp, which is essentially a group of threads, right? And then these thread blocks, once you compile your program, there'll be a bunch of thread blocks, right? Depending on how many threads that you end up declare. That thread blocks. So this is software, this is hardware. Anything below this line is hardware. Inside the GPU core, and don't listen to what NVIDIA try to brainwash you. Whatever they call a core is not a core. Whatever they call a core is I almost said bullshit, which I'll say bullshit terminology. Those are not core. Whatever they call CUDA core is this one execution unit, which actually is just one adder. A GPU core is a group of CUDA core. Whatever NVIDIA call SM or simultaneous multiprocessor, those thing is one core. So after you're done with at least this lecture, there's a lot of wrong things that NVIDIA try to advertise to you that are actually fundamentally not accurate in the academic sense, because we never actually define it that way, and it confuses people. It's misleading. But now, please remember, when you talk about GPU core, if you want to have the same analogy as a CPU core, these are the SM. The thread block is now mapped to each SM, right? As I show in this animation. And if remember the warp that I said earlier, that is this row of threads, the warp, each cycle you send one warp to this collection of execution units. This collection of execution units is whatever NVIDIA call CUDA core. Inside, it's just a bunch of adder or multipliers. It operates that operations on your data. But over here, if you look at this, there are 8 blocks, right? This is one instruction. You are running 8 different things. 8 different things inside the execution units. And this is dispatch. The thread block is now dispatched across different GPU core, right? So as I said, CUDA core is one execution unit. It's not an actual core. This is some misinformation stunt that I hate personally, and you should not do this if you're in academia. So I'm gonna make sure I correct this. So let's go back to our friendly 5-stage pipeline. Anyone remember this? Oh, so there's a question about thread per warp is equal number of execution units. Yes. Number of threads per warp is the same as number of execution units. Sometimes this is called a lane, because basically you fit in one car per lane. So this terminology, sometimes they use the word lane for the number of execution units. So let's go back to our friendly 5-stage pipeline. Remember this, right? It's whatever you have to do in the lab. Look at this complex diagram. In the CPU, in the high level, let's go high level overview of the CPU. What do you have? So we learned caching, right? We learned caching. So in the fetch unit, you have the instruction cache. You have the decoder. What is inside the execute units? Arithmetic and logic units. Whatever you have to do for adding, multiplying, those are in the execute stage. You have the load store unit, which handle the interface to the data cache and the memory, basically the main memory. And you have the bright back phase. What else did we learn? What are the other topics that we learned in class? What else? What was on the exam? Except aside from all these things. You have the branch predictor, right? You have logic that is for out of order scheduling. Another set of logic for out of order scheduling. You have on-chip cache. You have another logic for out of order processor. So what do you get from this? To run one thread, you're adding a bunch of things here. Just so that one thread is faster. And just so that one thread is faster. So many things are added to improve single thread performance. And yes, if you run only one thread on a CPU, I can guarantee you it's 99% of the time it's going to be a lot faster than running that one thread on a GPU. Right? Unless you do some weird thing with the code before you run into the on the GPU side, CPU is going to be a lot faster. A lot faster. All right. Another, I might sound like I hate the GPU. It is actually, in fact, I don't, right? My thesis, my whole PhD is on this topic. What I don't like is some of the PR and ads that I've seen nowadays that, hey, GPU is like magical silver bullet. No, it's not. Uh, uh, don't listen to marketing people. I mean, you're in computer science department, right? So you might have realized already that sometimes people in business do shady things that are not exactly like true. When you look at the scientific knowledge under what they say. So Over here on the CPU, many things are added to improve performance. Let's say I want to have a GPU. This is what actually happened. What can I get rid of? Any idea on things that I can get rid of to allow me to use the die, the processor die for something else? I can get rid of the branch predictor, right? I'll say, okay, fine, I'll do something with branch. I can get rid of anything that is built for out of order execution. I need to keep the register files, obviously, because you used to need to have that one for the programmer, right? What else? What else? Champ, what was your last question? It's about the number of execution units, right? So what I can do is, instead of having one set of ALU, I'll have 32 sets of ALU. I'll use the area for a bunch of ALUs. Because I want to do fine-grained multi-threading, I need to have a lot of register files entry, one for each lane, essentially. SRAM consume too much area on my processor. I'm going to get rid of it and add, well, not totally get rid of that, but have a software managed cache and the normal SRAM cache that we cover when we talk about caching, right? These things that are added is to improve instruction throughput. Why is that the case? You fetch, decode one instruction. Let's say I have 32 lanes. Let's say I have 32 lanes. How many operations I can do in one instruction? If I have 32 lanes, what's the maximum number of operations I can do? 32, right? I have 32 set of ALU, so I will be able to push in 32 things. So when you want to actually compute one instruction, this is done one instruction at a time. In what unit? One warp at a time, right? There can be many operations, but it's only one instruction. The benefit is many operations can be done in one cycle, and it's very high throughput, but it has to be the same instruction because it's one instruction at a time. The question that I'm going to have next is, if I don't have the out of order scheduling logic, how can I deal with instructions that take more than one cycle, right? How can I deal with instructions that take more than one cycle? It can take 5 cycles to do an add. It can take 25 cycles to do a multiply or floating point operation, right? So to deal with stall, this is what the GPU do. So this is the one SM, one GPU core. And before this, you've seen that there can be multiple warps inside the thread block, right? So let's say right now there are 4 warps. For the sake of my sanity, I need to draw something, and I don't want to draw too many boxes. Each of these small boxes is a thread, right? So when you run this, over time, a GPU becomes active. It take one of these warps, send that to the execution units. The way you run all these warps with one instruction on multiple pieces of data, what we call is a lockstep execution. One warp at a time. Warp G. When warp G is in the pipeline, you then switch to warp C. Then you switch to warp B so that you feed different warps instructions into the pipeline. And you notice this GPU core becomes active, right? So let's say warp A is a load instruction. It has to get data. How many data load will I issue? So my next question, if I have a load instruction in warp A, how many different pieces of data am I loading in that one cycle? There are 8 threads, so I'm loading how many? 8, yes. So because I have 8 threads, if I have a load instruction, I'm loading 8 pieces of data, right? And what happens if I have to load 8 pieces of data? Oh, it's going to take a while, right? So in the meantime, I'm gonna, because they're still active warps, the GPU core is still active. It still push warp D, warp C, and warp B into the pipeline, right? Until, let's say, out of chance, everything is loading. What happened? Now you have 32 loads. Everything is getting the data. GPU has nothing else to run until some of these comes back, until some of these warps data comes back. Then you can resume execution and remain active again. Any questions about how the GPU deal with stalling? This is essentially fine-grained multi-threading, but any questions so far? Because we are almost done with the conceptually how GPU works, and we'll slowly move into what can go wrong. Is one warp equal one instruction? Yes. It has to be one, basically it just has to be the same instruction. If the thread is doing an add, everything else in that warp has to be an add instruction. So because you only have one fetch, one decode unit. So the entire warp is fetched, the entire warp is decode before you spawn 8 different operations. Yeah, but that's a great question. Any other questions? All right. So what are the trade-offs? So now let's assume what we learned so far. This is essentially how the GPU is built. Sounds simple? Yes, it is. The actual micro architecture can be really complicated because they want really high throughput. The maximum number of instruction per cycle is number of GPU SM, number of GPU cores multiplied by lanes. This is what being described as CUDA core. It's going to have really turbo single thread performance because you don't have out of order scaling. There's no branch predictor. There's nothing to improve the single thread performance, right? So what does this mean? How do you get really good performance on your application? What are the big assumptions that you have to make to decide if you want to run something on a GPU or not? It means that you need to be able to do things in parallel, right? Somehow you need to spawn thousands of add operations that have the same program counter. So your program performance depends on the fact that application has to be super parallel. Then it will be really fast. Otherwise, if your code has a lot of critical section, a lot of sharing, and you can't really have one instruction covering multiple operations, then it's going to be really slow, right? Really slow. So the first use case is graphic application, right? And what I'm going to tell you, so how many of you have taken something like a graphic class before? Or is there a graphics class? Yeah? Okay. Oh, that's a great question. Yes, actually, both the GPU and CPU has a separate bus for memory addresses. So we'll go into that topic once we talk about the main memory, which is next week. We'll talk about that. So please wait a bit on that. But yes, the answer is yes. Why the GPU can't use out of order? That's also a great question. So if you go back to this slide here. So this is a CPU pipeline, right? And this is what we add for out of order execution and branch prediction. So I'm going to use the blue color. This is the logic you need for out of order execution. What the GPU do is, okay, this consumes a lot of your processor area. I'm gonna get rid of it. Basically, a GPU got rid of that. So your out of order, like what you learn and what you did in your exam, the last question on the pipelining and out of order execution, whatever those things are there on the CPU is now gone. That's why you cannot do out of order execution. The memory address parts mean the end that specify memory definition instruction, right? Yes. On a GPU instruction, the opcode is a little bit odd. Like you get what we call a PTX, which is the first version of assembly code, but depending on the actual model of the graphic cards, they have their own assembly, which we don't really know. Sometimes it's a black box that NVIDIA doesn't really tell us, but we can modify the PTX. PTX is like Intel x86 assembly. But the address part, there's a dedicated bus that connects to the main memory. The way it works in a CPU and the way it works in a GPU is similar. So the reason I'm gonna save the memory later is I kind of want to make sure I cover the processor side. And once we are done with that, I'm gonna cover the memory, and it will be a little bit more detail than again than the usual architecture class. So the research group that I graduated from back at Carnegie Mellon is like one of the top research. Like most of my friends do memory related research. I do that too, but on the GPU side. So we dig into the main memory quite a bit. The reason behind it because it's a big bottleneck. So we'll cover that next week. All right, so I'm gonna skip this animation because they are the same. Any other questions before we move on to the first use case? All right, so the first thing is, if you run graphic application or games, right? What do you have to do when you want to draw something? If you look at the pixel, right? The pixel that you have to figure out, okay, is this black, white, blue, green, red, whatever I need to show on the screen, each pixel are essentially doing the same operations. I need to figure out what goes on there. If you look at graphic pipeline in general, there are a lot of redundant instructions. Draw dots. Once you have all the dots, draw the triangles by connecting the lines together, right? So what is the common math operations when you need to draw a line? This is going back to your geometry day. What are the common math operations that you are required to draw a line? To compute like the angle of the line and to compute the location of the dots between each lines. Add and multiply, yes, exactly. So you have to draw thousands and thousands of lines. It's just a thousand of add and multiply, right? Then you need to convert from vector format, which is the actual location of the line and how the line, like how long the line should be, into bitmap. We call that rasterization. Then you smooth out the surface, right? You don't want your model to have a lot of triangles. You want to smoothen out. Those operations also a bunch of add and multiply, a bunch of comparisons. Then you draw a surface, right? You do what we call texture mapping. You have a texture and you map the texture on the shape. And because Just to be aware, I'm not a graphic expert. I never take a graphic class. So this is kind of like roughly the idea, like how much I know about graphic rendering and graphic pipeline. But basically, once you have the shape, you map the texture on the surface. And then if you have a lot of surfaces and objects, what do you have to do? Your screen eventually does kind of like a 2D thing. So you are looking from the perspective of your eye. So from your eye point of view, you need to figure out from the camera point of view, what object to be shown, what object are partially occluded, right? So that also a bunch of comparison. Then you compute lightning, right? This is one of the most important applications. Yeah, ray tracing is actually one of the really, really complex operation. But the way it works is the way it works in ray tracing, if I understand correctly, please correct me if I'm wrong. But basically, let's say in your scene, you have three light sources, right? Three light sources. Ray tracing basically allows the three light sources to generate ray of lights, and you just allow them to bounce in the environment for a lot of times. Those bounces will calculate basically what has to be shown on each surface, right? Something like this. So if you look at ray tracing, it's something like this. Let's say you have a light source right here and light source here. So it allows you to calculate this how the ray bounce around, right? Each time it bounces, it loses energy. So each time it bounces, it's going to kind of like blend, not blend, but like has less and less intensity. Anyone want to take a guess what happened if sunlight goes into my skin? Does it bounce like a mirror, or does it kind of like absorb into your skin a little bit before it bounce out? It absorbs, but it doesn't fully absorb it, because if something is fully absorbing the light, what does it mean? From your eye, what does it mean in physics? This is like back in high school physics. If an object absorbs the light completely, yes, black hole, it should be black, right? But your skin is not black. It means that it goes into your skin, it bounces around a few times before it bounces out. That's why you have this not exactly like a mirror-like surface area where lights come in and it bounces out right away, right? And then with ray tracing, you then have the camera right here that observe what is the light that goes into the camera, so that you can render the scene in a really, really photorealistic way. And this is really, really compute intensive, actually. It's a bunch of if else. Actually, if you convert this, it's so many if else, right? And it can be complex even on the GPU, because if else is not really exactly the friendly thing on the GPU. And then we'll go into why. But in general, graphic application, there's a lot of basically repeated operations, and these are done in parallel, right? Okay, so let's talk about if else now that I talk about, hey, if else is not exactly friendly toward GPU. So let's look at this warp at if a equal 0, right? And for the sake of sanity, I'm gonna have the blue color for the true A0, and the red color means that the A equal 0 return false, A is not 0. What does it mean to this warp? If I told you that, I told you earlier, right? The warp has to finish the the same instruction at the same time. Now our predicated execution comes into play. What do you do if A is true? The first thread, the second thread, and the fifth thread would run, right? It would run whatever do something is. The other 5 threads, you insert bubble. You don't run that. In the GPU, there's a mask. There's a mask for your operations. And basically that mask determines if it's a 1, you run it. If it's a 0, don't execute that. So these masks would disable these threads, even though the PC, the program counter, is at the do something. Then when this is done, you will basically finish up the first 3 threads, and the other 5 threads is doing something else, right? What happened? What is the main problem here? Will you ever, right? Will you ever get fully 5, like all these 8 threads to execute at the same time? Is it possible such that everything in here, all the 8 threads, is executed together? Would that be possible? You can use to actually that's one of the paper idea that was presented at this is one of the top architecture conference back in 2011, if I recall correctly, or 2010. So your idea is actually it's a paper. But in fact, it's yes, you can actually do it. The only two condition is if everything is true. If everything is true, you do something, done, right? Or if everything is false, and false, right? These are the only 2 things that would allow the thread to go together. So this problem is called branch divergence. So from the earlier example, you do not actually like utilize, right, all the execution units at once. This is called branch divergence. And basically, if you look at this diagram, instead of having 8 operation per cycle, right, 8 operation per cycle, what do you get? Something between 3 to 5, right? Depending on what dominant. If do something is longer, you will then get closer to 3 instruction per cycle. If the false part is longer code, then you are doing something closer to 5 instruction per cycle instead of 8. So this reduces GPU performance. And here's some example that can be true, right? Consider this example. Assume that each GPU core has 64 lanes and load store is somehow magically free. What is my GPU core utilization? So this is like a mini in-class exercise. I have I going from 0 to 1024. And if A of I mod 3 is 0, you do if, otherwise you do else, right? So let's go through this together. So the first thing you have to realize, this depends on A of I, right? Which we haven't assumed anything yet. But if A of I does not really, so let's say A of I is I. What will we get? What will we get? So how about this? Let's take a quick break and we'll meet at 1:30. And you think about this, you all please think about this question a little bit, because I can guarantee you some form of this kind of question will be on your exam for the final. But the hint, right? Hint. Basically, because we just talk about branch divergence, look at branch divergence and see what's the percentage of the thread that do this versus the percentage of the thread that do the second line. So let's take a break with this question, and we'll resume once we are back. We'll talk a little bit about this question, followed by the checkpoint. All right, so we meet at 1:30. Is that okay? We meet at 1:30. I'm gonna talk about the solution to this question, and then we'll switch over to the checkpoint. All right. We'll see you all in a few minutes. All right, so are we back? So I'm gonna do the first 0 to 63. The rest are basically following the same logic with a slight difference because this is divisible by 3, not 4. So 64 is not exactly divisible by 4. I mean 3, my bad. So if you look at this, there are 4 instructions. 1, 2, 3, and 4. Inside the if else, right? Let me close the door real quick. Sorry, my niece was crying outside. So, all right, so let's continue. There are 4 instructions. Each instruction, because there are 64 lanes in total, in the denominator, you have 64 multiplied by 4 because there are 64 lanes, 4 instructions. For instruction one, how many? What's the utilization inside instruction one? Are we running on all lanes? Because it's just a compare, right? So the instruction one is 64. There are, for A of I, in this case from 0 to 63, there'll be 22 of those that A of I modulo 3 becomes 0, right? That becomes true. So this is instruction 1. This is instruction 2. Plus, for instruction 3 and 4, right? Instruction 3 and 4, they would look the same. Essentially, this is going to be, what is 64 minus 22? That's 42. Multiply by 2, right? Because there are 2 instructions that has 42 threads executing in the else statement. So basically this is our utilization for I equals 0 to 63, right? And you can repeat this until 1024. There'll be a repeated patterns once you add, I think 9, not 9, 64 multiplied by 3. So that's 192. Everything will repeat. So you then get the GPU core utilization. Any questions on how to proceed and why do I arrive at this conclusion for I is 0 for I between 0 to 63? All right, and don't jump on a tissue paper, please. Any questions, or are you not back yet? Am I going too fast? On Wednesday, we'll continue on talking about how to handle data accesses, which is another big topic on the GPU. Right? Similar to the CPU, GPU also have the typical memory hierarchy, and we'll talk about how to handle data accesses. There's a chance I'll talk about the main memory before this, or depending, let me decide a little bit, but on Wednesday, we'll continue on to talk about the memory part. Then for today, because as promised, I will have a checkpoint for all of you. So let me unshare this and move over to Discord. Are you all here? So that we can do the checkpoint. Okay, so let me stop recording.